where we're going to be covering the second part of lesson 2, the quantum theory of the atom. So this is going to talk about our current model of the atom, which we call the quantum mechanical model. And this model is done really well in explaining a lot of different things. It's never been proven wrong. So first, we're going to talk about Heisenberg uncertainty principle. This was covered in another lesson, but we can't know the exact location and the position and the velocity of an electron. So we can't think of electrons as orbiting the nucleus the way that Bohr said. So now everything is going to be based on probability. So Schrodinger was the person that started to think of, de Broglie was first, but Schrodinger was able to write some mathematical equations, solutions to wave function equations, and through that was able to develop the current model of the atom. So the current model is called the quantum mechanical model, and it does treat electrons as being waves. Sorry. If you remember, Bohr's model works for hydrogen, but not other elements. Schrodinger's model works, or this model that Schrodinger helped create applies for every element. So the first thing is an atomic orbital is a three-dimensional space where somewhere around the nucleus where the electron is likely to be found. So each orbital can hold up to 2 electrons. So the picture here is just kind of showing you the dots represent where an electron is at any given time, like if you were going to take pictures of where they're at over and over and over. And you can see that they're more dense and more likely to be found towards the nucleus, and less likely, but still a possibility, way outside. So really about a 90% chance that it'll be inside of this boundary. And that's what all of the model is just thinking about the probability of electrons being in these different locations that I'm going to show you. So there are 4 quantum numbers. The quantum numbers are kind of give us a description of where the electrons are likely to be found, not where they are exactly. It's kind of like an address, like you live in Minnesota, your city is Eden Prairie, you live on a certain road, and then you have your house number. So each one gets a little bit more detailed. So we'll talk about each one of those in just a second. So the 4 quantum numbers, this is one of them. This is the principal quantum number. We use the letter N for this. So as the N value gets larger, then we're talking about more energy or further from the nucleus. So this is a Bohr model, but this does still really help illustrate that as your N is getting bigger, you're getting further from that nucleus. This is just kind of almost the same thing. This is just talking about, so over here, it's hardly any difference. So a principal quantum number is the relative size and energy, whereas the N, the principal energy level, is the actual major energy levels of the atom. To me, I think they're kind of the same thing. So anyways, though, within each energy level, and you will find an equal number of sublevels that have slightly different amounts of energy. So for example, it's kind of like a house. Like if I were to walk in, this is the ground of the house or where the nucleus is. When I get to the first level of the house, there's just one level, nothing new. But then when I get to the second, there's 2 slightly different sublevels. So 2 different floors that are just a little bit different in height. And then N equals 3, there's going to be 3 separate sublevels, and so on. So here's where this corresponds to a note sheet that I would fill out with me. Here's where I'm going to talk about each one of the 4 quantum numbers. So the first thing is on your sheet, I don't think you have the periodic table, so I'm just going to sketch one for you. So the periodic table and the quantum numbers are directly related. So the principal quantum number, remember, that tells us which energy level we're in and how far away from the nucleus we are. So if you look at your periodic table, or if you just want to sketch this in your notes, that first row or period is n equals 1. So those elements all have electrons that are only in that first level. N equals 2, these elements are going to have electrons in the second energy level and the first energy level. N equals 3, they're going to have electrons in the third energy level, but also the second and the first. So the levels below it are also containing electrons. So that's one thing. And then the other part, just so basically this principal quantum number n tells us the energy level, and it indicates the distance from the nucleus. So how do I figure it out? It's the same as the row or period on the periodic table. So the options are like we were just writing, all the way to n equals 7. So the next quantum number is the angular quantum number. It's kind of a loopy L. And this is going to tell you how many sublevels. So if L equals 0, we're going to have the spherical, this right here, shape sublevel. Actually, so it doesn't tell you necessarily how many sublevels, but it tells you the shape of the sublevel. If you have a value of L equals 1, then you're going to be talking about these dumbbell shapes. So these are, if you think about like a dumbbell, that it's in the X, the Y, and the Z directions. So those are called P dumbbells. If L equals 2, then we're talking about these blue, which are the D sublevel shapes. And then if L equals 3 and L only goes to 3, then we're talking about this last group where they're really pretty intricate, so we call them fancy. So how do I figure out the angular quantum number L? I realize that L is going to go from 0 to whatever the n value is minus 1. So, for example, if n equals 1, L equals 0. So in the first energy level, I'm only going to have that spherical shape. If n equals 2, I'm going to still have the L equals 0, but I'm also going to have L equals 1. So I'm going to have another 2s. This would have been 1s. So another S shape, but in the second energy level. And now I'm going to have the P, which we'll call the 2Ps, because they're in the second energy level. When n equals 3, we're going to have, again, L equals 0. So we'll have a 3s, a 3p, a 3d. So you'll see the d's appear for the first time. So when you get to the third level, there's these 3 different sublevels. And then if n equals 4, then we're going to have L equals 0. So you'll have the 4s. L equals 1. So you'll have 4p. So 4 just means we're in the fourth energy level. L equals 2. So we'll have a 4d. And L equals 3 means we'll have 4f. So we're going to have all 4 of those shapes in the fourth energy level. So I was going to show you something. Let me see if I can do that quick. So I was showing these videos can kind of help. So let me show you one. I'm going to turn the volume down. Showing you what I'm like, and it's 3-dimensional. And then the next one, That one is L equals 1. So you see the orange, the red, and the yellow are each like dumbbells. So there's 3 of them, and those occur when you get to the second energy level. The D, remember there, if you look at your note sheet, there's 5 of them, and they don't appear until n equals 3. So there's not going to be like 2D because the D um, doesn't occur based on the L values. So um, that is so instead, when I was talking about the house and kind of the different levels, when you go into the first level, you're only going to find that one sphere. If you go to the second, you're going to have the sphere and the dumbbells. If you go to the third, you're going to have a sphere, dumbbells, and the D shape. So I'll keep explaining. I'm going to do the next quantum number. So there's 4. We've done 2. So the fourth one is the magnetic quantum number. It's m sub L. How do we determine it? It's negative L to positive L, including 0. And what does this one tell us? It tells us really how many orbitals are there. An orbital, remember, can hold up to 2 electrons. So it's really how many ways can the that shape be in space. So let me show you. So if L equals 0, we know we're talking about that sphere, right? Then m sub L is also 0. So there's really going to only be one orbital, which can hold up to 2 electrons. So you look at your shapes here, the S can only be oriented one way in space. So it's going to only have one orbital. So it can hold up to 2 electrons. The next one, if L equals 1, remember we're talking about the P, those dumbbell shapes, then m sub L, the magnetic quantum number, is -1, 0, +1. So notice there's 3 different numbers there. So there's 3 orientations, or we would say there's 3 orbitals whenever we're talking about a P sublevel. So when we look at our P here, notice there's 1, 2, 3 of them. So 3 orbitals means these can hold 1 orbital for the S. So the 3 orbitals can hold up to 6 electrons. So we'll keep going. I'm just going to change this a little bit, and then we can add to this. So the next L value would be L equals 2. So now we're talking about the D. So m sub L is going to equal -2, -1, 0, +1, +2. So notice there's 5 orbitals essentially for the D shape. And again, if you go up here, the D has 5 different ways that it can be in space. So then the next one, we should get 7, because then you see there's 1, 2, 3, 4, 5, 6, oops, 7. I counted on the wrong side. So we should get 7 when we solve for m sub L. When L equals 3, we're talking about the F. We're going to have -3, -2, -1, 0, 1, 2, 3, 7 orbitals. So the F shape can hold up to 14 electrons. One last quantum number, and then we'll do a couple examples. This is the spin. So in the orbital, if you remember, every orbital can hold 2 electrons. When the 2 electrons are together, they're going to spin in opposite directions. So they're going to either spin up, and we represent an electron with an arrow, or they're going to spin down opposite each other. Again, that's just each arrow means an electron. And the direction is the spin. So the value of the quantum number, the spin quantum number, is either positive 1/2 if it's spinning up, or negative 1/2 if it's spinning down. So let's keep going. I'm going to give you, so this should be a loopy L, a couple examples. So the numerical value of N and L. So 3s means I'm in the third energy level. So it's like 1, 2, now we're the bigger, further from the nucleus, 3s, or yeah. And then it's S, so we know that L is 0. Next one, again, the 4 means we're in the fourth energy level. And F, remember the L value for F is 3. And then we have the P. So this one, we're in the second energy level, and L equals 1. So we'll do another one. So then how many orbitals in those same ones? So remember, N equals 3, L equals 0. So orbitals, this one has 1 orbital, because back to our, we don't have to do the m sub L again, but our m sub L value, there's only 1. For F, remember the F's, if I were to do it, I don't need to do it again, but -3, -2, -1, and so on, I would get 7. So 7 orbitals. And then the 2p, I'm in the second energy level, L is 1, and then remember there's 3 orbitals. So how many max electrons? It's just going to be however many orbitals times 2, because each orbital can hold up to 2. So the 3s can have up to 2 electrons. The 4f can have up to 14. And the 2p can have up to 6 electrons. So let me show you one more thing that I think can help with the understanding of this. It's another video, and it's this one. Second. Okay. So this is showing now what goes on in terms of the electrons. This is scandium. There's 21 electrons. So this is the 1s. So remember, we're in the first energy level, L equals 0. There's 1 orbital. It can hold up to 2 electrons. 2s, so it kind of looks like, ooh, it's bigger. It should hold more, but it still only has 1 orbital. It can only hold 2 electrons, but we're in the second energy level. Now come the 2p. So remember, there's 3 orbitals, so there should be 3 of the p's that come in, and they can hold up to 6 electrons. So notice how everything kind of overlaps, centering on the nucleus, which would be where those all of those intersect. So the next is going to be even bigger. It looks like it should hold a whole bunch, but it's an S. L equals 0. There's only 1. M sub L equals 0, so there's only 1 orbital, so only 2 electrons. These 3 p's look big, but there's only going to be 3 of them, so 3 orbitals, 6 electrons. They're just further from the nucleus when the number gets bigger in front. So similar to the 2s, but they're bigger and further from the nucleus. I mean the 2p, sorry. And here's 4s. It looks like it's, very big, but again, it's just far from the nucleus. It still only has 1 orbital, and it can hold 2 electrons. Here's the Ds. Remember, there's 5 orbitals, so there should be 5 of the D, shapes that are going to come in. And so far we're at 2, 3. So orbitals are equal to how many there are going to be? 4. And 5. So really, all of these sublevels are overlapping so that you can see that the atom, essentially it becomes like a sphere, but remember the electrons are in those three-dimensional shapes. Each shape has one orbital. So they're not orbiting. And I'm trying to get us out of this. I'm done with the video. Okay.